Let's talk about inverses, inverse relations, inverse functions. Let's get to it. Okay, an inverse relation maps output values back to their original input values. It's basically taking us completely backwards through a function or relation. Instead of plugging something in and getting something out, what if we wanted to do that process backwards? Take those outputs, plug them into something, and get back the original input. That's what an inverse relation does for us. Okay, so that's what we're talking about today. In other words, our x and y's, our inputs and outputs, end up being swapped in an inverse relation. The notation we use for the inverse of a function, so let's say it's called f of x, is written as f inverse of x. So this little -1 that's written up here as a superscript, kind of like an exponent would be, is just notation. So this is f inverse of x. Okay, so there's our notation. If a relation and its inverse are both functions, if they would both pass our vertical line test, or every x has exactly one y, they are called inverse functions. Okay, but that's only if both a relation and its inverse qualify as functions. We call them inverse functions. You don't have to worry about this too much. Okay, so let's do an example. Here is a function g of x defined below in a table. And it says what are the points, or asks us what are the points on g inverse of x. Okay, so we notice we have some points on here. 1, 7, 2, 10, 3, 13, 4, 16. 4 different points in this function g of x. Okay, so what are the points on our inverse going to be? Well, remember, in our inverse function, we're going to have a table where I want to plug in these values. Apologize for my lines here. We want to plug in these values that we originally got out. So I want to plug in 7, and I want to get back 1 for y. I want to be able to plug in 10 and get back the value of 2. And of course, I want to be able to plug in 13 and get back a value of 3. And I want to get back, plug in 16 and get back a value of 4. Okay, so the inverse g of x should look like this. And again, you might notice from our definition that really the only two differences between these tables is that the x and y values are swapped. Okay, so how would I find a function that would take me backwards? How would I get a function that would give me back those values? And it's actually a lot easier than it sounds. Okay, to find an inverse equation, first thing we're going to do is replace any function notation with y. So if it says f of x or g of x, whatever it is, we're just going to replace it with y if necessary. It might already say y equals. Okay, then to find our inverse, we're going to swap x and y. We're going to change our input and output variables. Don't change any values associated with them, just literally write y where x was and x where y was. Okay, then we need to kind of quote unquote solve for y here. We need to get y by itself and positive on one side of the equation. It doesn't matter which. Okay, so let's try an example. For g of x equals 3x plus 4, find g inverse of x, or the inverse of g of x. Okay, so running through our steps, step 1 is to replace f of x with y, in this case g of x. So we're going to come to this top function, and where g of x is, we're going to write y, and then we're going to write the rest of our equation equals 3x plus 4. Okay, step 2, really important when we're finding inverses, swap x and y. So instead of y equals 3x, we're going to have x equals 3y plus 4. So y became x became y. That's step 2. Don't change any of the numbers. Don't bring the 3 over here with the x. Okay, it stays put. And lastly, we need to get y by itself. Okay, so to do this, to get y by itself, we need to get rid of these two values held onto y here. Let's first subtract 4 over. X minus 4 equals 3y. And then divide everything on both sides by 3. So we either have y equals x minus 4 all over 3, which would be acceptable as an answer, or you could also separate them as the value in front here, 1x divided by 3 is the same as 1/3 x minus 4 over 3. And the only reason you might write it in this form is it looks more like an equation of a line. However, if you're plugging in values, the version we had over here, which was x minus 4 all over 3 equals y, these are both acceptable values. They're both correct inverses here. This just looks more like y equals mx plus b form. So good to know that we can have either one. Okay, let's try our next example. For f of x equals 5x minus 10, find f inverse of x. So once again, step 1, replace f of x with y. Step 2, swap x and y. Step 3 is we need to get this y by itself. So we're first going to add this 10 over to the other side. X plus 10 equals 5y. Of course, those cancel. And divide everything on both sides by 5. Okay, so I could write this as x plus 10 all over 5 equals y. Or, again, you can think of there being a 1 here. So this is really the same as 1/5 x plus, well, 10 over 5 reduces to 2. And so here is 2 acceptable answers for our second question. X plus 10 all over 5 equaling y, or 1/5 x plus 2 equals y. Okay, so a question might be, how do I actually know if these are the correct inverses? Well, one thing you can do is, let's say I want to plug in a value. I'm just going to pick an x value randomly here. Let's plug in 1 to make it easy. So I was going to plug that in. 3 times 1 is 3, plus 4 is 7. So in this original function, when I plug in 1, we get back 7. Okay, so what should be a point on my inverse then? Remember that the x and y coordinates swap. So let's check if we have the correct inverse. And I think the second version down here is going to be easier to plug into. So remember in the inverse, if I plug in 7, we should be getting back 1. So let's plug in. 7 minus 4 is 3. 3 divided by 3 is 1. Hey, look at that. Looks like we have the correct inverse. You could arbitrarily pick a nice easy point here as well. Let's say this time we plug in 2. 5 times 2 is 10. Minus 10 is 0. So plugging in 2 gives us back 0. Sorry for a crummy 0 there. So on our inverse, if I plug in 0, I should get back 2. So let's check. If I plug in 0, in fact, it doesn't matter which one this time. Let's try this one. 0 plus 10 is 10. 10 divided by 5 is 2. 0, 2. So we definitely have the correct inverses here. Okay, let's do our last example here. This time it's giving me a slightly more difficult one to work with. We have a quadratic. But again, let's go through our steps. So we're replacing h of x with y. Swapping x and y. And then getting this y by itself and positive isolate y. So we're going to start by adding 2 over. X plus 2, that's a 2, equals y squared. And now remember, to undo an exponent when something is squared, we use the square root. That's the opposite operation here. But remember, when we have something that's squared, we also get 2 possible cases. So we really end up with plus or minus the square root of x plus 2 being equal to y. And so in fact, you'd actually have to graph this as 2 separate equations to get the full inverse relation. And because if I plug in a value for x, we're going to get a plus case and a minus case, this is actually not a function. The inverse of this graph would not be a function. In fact, the original will be. We'll look at this graph in a little bit, but its inverse is not. Okay, so in fact, let's take a look at the graphs of the previous 3 examples and the inverses we found. So we're going to check out and see if we can see something that happens graphically. Okay, so here's a lot of information. We've got a lot of graphs going on here. But know that each one of these examples we just did, g of x, f of x, and h of x, these are the same three graphs that were on the last slide. And the original functions are all in blue, and their inverses are in red, or in this case, when I had to graph two different parts, red and green, the positive and negative case there. Okay, so do you see anything that relates each of these original graphs in blue to the graphs in red? Okay, or red and green, the inverses here. Okay, and at first, it's not super likely that you see it. Okay, but what I'm going to do is we're going to graph the line y equals x. Okay, and so that's done here in yellow. Y equals x. That's the line graphed right here. That's a line with a slope of up 1, right 1, and a y-intercept of 0. I've also added some points that are on the original graph and its inverse point for emphasis. And maybe now the relationship between these two is a little more obvious. Okay, in fact, I'm going to add in the other graphs here, also with some points in our line y equals x. And see now if you see a relationship between all of them. If it's not apparent yet, the answer is that each of these graphs is reflected over this line. This is a line of reflection for graphs and their inverses, y equals x. Which kind of makes sense, I guess, because we're switching x and y, so the line where x and y are exactly equal ends up being kind of a mirror or focal point for a mirror. Okay, so all inverses are reflected over this line y equals x. Make sure you have that in your notes, that's important. We'll definitely see some questions that go along with that. Next, we're talking about function composition or composition of functions. Okay, so what does that mean? What is a composite function? So it's a function basically that's composed of two functions. So we'll read our definition here. It says when two functions are combined so that the output of the innermost function becomes the input of the outermost function. And that sounds pretty confusing. This is technically a correct definition here. A much easier way of saying this is when we plug one function into another function. Okay, so let's talk about notation when we're doing plugging a function into another function. Okay, for two functions, f and g, the composition where g is plugged into f will look like this. So g is being plugged into f. So we'd normally write f of x. It's now f of g of x. G of x has been plugged into f of x. Okay. There are a couple other ways of notating this. You might see this written as f of g, and they use this kind of open circle here. So this doesn't mean multiplication. It's not the letter O. It's like a little open circular dot. And that's used for composition only, f of g. Alternatively, you might see f of g of x. Okay, these kind of mean the same thing. Mostly we'll be looking at these two. You'll see this open composition dot, or we'll see one nested inside of the other. Okay, so let's do some examples with function composition. So here we have three defined functions, f, g, and h. Okay, and they're in blocks just to make them easier to reference. So our first example wants us to find g of f of 2. Okay, so what we want to do first when we're evaluating functions, if they're giving us a value to plug in, is we always want to evaluate the inner function first. So the first thing we need to find is what is f of 2. So we're going to take the function f, 2 times x plus 4, or we're going to replace x with the value we want to plug in, which is 2. So 2 times 2 is 4, plus our other 4 gives us 8. This inner function evaluates to 8. So we can think of this as now turned into 8. And to finish answering our question, the output of this function, function f, is what we're going to plug in to function g. So that's kind of where our confusing definition comes in up there. So we're just going to take our answer of 8 and plug it into the outermost function g. So we need to find g of 8. So function g is here. 3 times x minus 8. And again, we're replacing x with the value we want to plug in. Okay, so we're using this 8 to plug in here. So 3 times 8 is 24, minus 8 more is 16. G, of f of 2 equals 16. Yeah, so 16 is our final answer here. That's what the value it was looking for. Okay, let's try the last one in this section. Okay, find f of g of 2. So the first thing, again, we're going to start with our outermost, or evaluate, the innermost function g of 2. So we'll go to function g, 3 times x, we're plugging in 2, minus 8. 3 times 2 is 6, and 6 minus 8 is negative 2. So this innermost function has evaluated to negative 2, and that's what we need to plug into the outer function. So we're going to find f of negative 2, again, plugging in this value to the outermost function. And you always work from the inside out with these. So if they had, like, I don't know, something crazy like f of g of h of x. Crazy. You find h of x, get that answer, plug that into g, get that answer, plug that into f. You just have to work from the inside out. Okay, anyway, back to this. We're plugging in negative 2 to f, so 2 times negative 2 plus 4. Again, we're just using the definition from f up here, and plugging in negative 2 for x. Gives us negative 4 plus 4, which gives us 0. F of g of 2 gives us 0. So notice in these two, we plugged in positive 2 to both. The only thing we did was change the order. Did we get the same answer? Definitely not. So what does that mean? Order matters when it comes to function composition. Plugging in one way or plugging in the other can give us two completely different answers. So we need to make sure that we're paying attention to the correct order. Okay, so we're going to use these same 3 examples. This is just the same as the previous page, just here for reference. And let's find one more evaluating. This time, we're trying to throw us off a little bit by plugging a function into itself. But again, let's just follow our steps. We're going to start with the innermost function, g of negative 1. So that's 3 times negative 1 minus 8. So that gives us negative 3 minus 8 more, or negative 11. Okay, so our innermost function evaluated to negative 11, and that's what we're going to plug in the outermost function. It just happens to be g again. So we're going to do 3 times negative 11 minus 8. Again, of course, for both of them, we're stealing that from up here. 3 times negative 11 is negative 33. Minus 8 more is negative 41. So our answer for g of negative 1 is negative 41. Okay, let's do our next example. Find f of g of x. And you might notice this time they didn't give us a number to plug in here. Instead, they've just given us the variable. Okay, so we're not going to evaluate. In fact, what we're going to do is actually plug one function into the other and simplify the expression. It's going to look like an expression like on the right of these. Okay, this time, we're actually going to start with the outermost function, f of x, which is 2x plus 4. Okay, I just like to rewrite it to have it there for reference. And we find f of g of x, and I'll try to keep this color coordinated for you here. So let's do f of g of x. Apologies here. Okay, f of g of x. That did not change color. G of x equals 2 times parentheses where x was, and we're giving ourselves some more room here because this time we're plugging in that expression, g of x. So the expression for g of x is 3x minus 8. Okay, so what we need to do here is go ahead and distribute our 2. It's 2 times this entire quantity. So again, this is where it's important to make sure you're using parentheses when you substitute in. This time we did need to distribute. 2 times 3x is 6x, 2 times negative 8 is negative 16, and then we still have our plus 4. Again, the last step is just to simplify. We do have a couple like terms, a couple constants over here to combine that gives us negative 12. Okay, so f of g of x is equal to 6x minus 12. So if we go back for a second, we actually did f of g of 2 in the previous page. Okay, f of g of negative 2, or sorry, of 2. We plugged 2 in, we got back 0 in the end of this process. If you notice here, we did the same composition, we just didn't plug a number in. But this expression we just got will actually give us the same answer we got there. So if we kind of repeat what we did with 2, if I wanted to find f of g of negative 2, and I've already simplified this expression, I can actually just plug in, positive 2 is what we plugged in. 6 times 2 minus 12 is 12 minus 12, or 0. We get the same value back for both. So you can either just plug the number directly in, which I think is easier, and do it in 2 steps, or you can simplify the expression and then plug into that expression. We'll still get the same final value. Okay, similar here. This time it's using this new notation for us. Find g of h. So remember, this means the same thing as g of h of x. So once again, we're going to start with the outer function, g of x. Okay, from the top is 3x minus 8. And now we're going to plug in h of x into it. So g of h of x will equal 3 times x minus 8. Okay, trying to be a little smarter about changing colors. So g of h of x. And h of x is 2x squared minus 5. So that goes in our parentheses that we've replaced x with. Again, always use parentheses there. So we'll need to distribute our 3. That gives us 6x squared minus 15 minus 8 out here. And combining our like terms, our negative 15 and negative 8 make negative 23. So g of h of x simplifies to 6x squared minus 23. Okay, last example here. This one's going to be a little more painful. Okay, so this time it's asking me to do h of f. So just like we read it out loud, h of f. And if they don't specify a number to plug in, it just means of x or whatever variable. So we're doing this. So again, we'll start with the outer function h, which is h of x, 2x squared minus 5. So we're going to do h of f of x, which will be 2 times our x value squared minus 5. Okay, and what we're plugging in, of course, is the function f of x, or the expression for f of x, which is 2x plus 4. Okay, now this time I cannot distribute my 2 first. Remember, order of operations, I need to evaluate my exponent. And of course, 2x plus 4 squared means times itself twice. So I'm actually going to write that out. Okay, so I've done my exponent, and now we have a lot of multiplication to do here. When you multiply things, you can do them in any order. So you can multiply these three in any order. I'm going to choose to multiply, or kind of FOIL those two together first. Okay, 2x times 2x is 4x squared. 2x times 4 is 8x. Distributing the 4 now, 4 times 2x is another 8x. 4 times 4 is 16. And we still have our minus 5 out here. Okay, so I can combine these two. Gives me 4x squared plus 16x in the middle, plus 16 minus 5. I still need to distribute my 2 through everything, so let's do that. That gives me 8x squared plus 32x. And distributing my 2 way over here gives me another plus 32 minus 5. And wow, we're starting to really run out of room at the bottom here. Just barely squeeze it in. We have 8x squared plus 32x. And combining our constants, we get plus 27. So of course it's a little more painful because we had to multiply that polynomial out, or square 2x plus 4. But there's our answer for h of f of x.